we saw the common ion effect, which affected our acid-base calculations earlier. We have similar issues when using or dealing with the solubility of compounds. So, as an example problem, what is the molar solubility of silver bromide in 0.0010 molar sodium bromide, given this KSP of silver bromide? All right, so consider that in this sodium bromide solution, which is well soluble and hence gives us a already significantly high concentration of bromide, we're going to have to calculate how far the silver bromide dissolves into silver and bromide ion. Now, there's already an initial concentration of bromide here. There is a common ion here. And having this common ion here, this is going to affect how far this reaction proceeds. You can see that having a lot of bromide here already, the reaction should be shifted to the left somewhat, so that not as much silver bromide will dissolve, or silver ion will be dissolved either. So we can view that in Le Chatelier's principle, or we can calculate as well. So using a nice table, we can plug in that that KSP, 7.7 times 10 to the negative 13, is equal to S, which is the molar solubility of silver, times 0.0010 plus S, which is the molar solubility of bromide. But being that we have a common ion here, there should not be a very significant reaction. And having such an insignificant reaction, having it occur so little, this positive S, this plus S, should be almost negligible, and so we can cross it out. And so we can now just consider that the KSP is very nearly equal to S just times 0.0010, ignoring the plus S. And so being almost equal to, very nearly equal to, 0.0010 times S. So you can calculate the molar solubility here, and hence the concentration of silver as well, as being 7.7 times 10 to the negative 10 moles per liter. But if there had been no common ion present, if bromide had not already been dissolved in solution, the molar solubility would have been 8.77 times 10 to the negative 7. It would have been 1,000 times bigger had bromide not already been dissolved. And so we can see that adding that common ion decreased the solubility significantly. But this also, this effect also is large part of how pH can affect solubility as well. First, consider the pH and the concentration of magnesium in a saturated magnesium hydroxide solution. Magnesium hydroxide has a KSP of 1.8 times 10 to the negative 11. You can calculate that in this solution. The value of S is 1.7 times 10 to the negative 4, which is the value of magnesium. But also that the concentration of hydroxide is twice that. It's 3.4 times 10 to the negative 4, and so the POH is 3.48 and the pH is 10.52. All right, so these are our initial concentrations of magnesium and the initial pH. But what if you tried to dissolve magnesium hydroxide in a buffered solution at pH of 9, in a more acidic solution, less basic? Having a less basic solution than we did in that saturated solution, decreasing the concentration of hydroxides in that solution, we should expect that the concentration of magnesium which dissolves is going to increase, being that the reaction should shift to the right by removing this product. So find the concentration of magnesium here, solve for S again, except this time we have a common ion present, hydroxide already present, and we're able to cross out that common ion in our calculations, saying that S is about equal to 0.18 molar. And we saw, therefore, that initially the concentration of magnesium was 1.7 times 10 to the negative 4 molar in just dissolving magnesium hydroxide in just water. But having this buffered solution, which has a lower concentration of hydroxide than in the previous case, we have much more magnesium dissolving, about 100 times more. We can see that, yes, by decreasing the pH from that 10.52 to the 9.0, we made the solution less basic or more acidic. This decreased the concentration of hydroxide, this shifted the reaction to the right, and hence increased the concentration of magnesium which could dissolve. In further problems which don't involve much math, we could discuss dissolving a compound, say lead fluoride. Is this more soluble in acidic or basic solution? All right, so lead fluoride dissolves to give lead ion and 2 fluoride ions. Now, are either of these affected by the presence of protons or hydroxides? Very, very occasionally, the cations will be precipitating in the presence of hydroxide. More commonly for problems like this, the question is acid going to affect the solution? Is the increased concentration of protons going to affect the concentration of anion? So here you know that the fluoride does react with protons to give hydrofluoric acid. We know this reaction can occur significantly. You can form hydrofluoric acid in presence of water. This is a weak acid. So fluoride does react with protons. And reacting to form HF, this decreases the concentration of fluoride, which shifts the reaction more to the right. We can see that this dissolving of lead fluoride increases. It's more soluble if we consume that fluoride by having an acidic solution. It's more soluble in acidic solution. What if we had done a similar problem, except in this case we had used lead chloride? Well, lead chloride should not be affected by whether you have a acidic or basic solution, because you know that chloride should not react with protons in solution to form hydrochloric acid, a strong acid. That reaction should go 0%, not at all. It's negligible. And so neither protons will react with the chloride or hydroxides react with the lead, and so there should be no effect. There should be no effect of protons or hydroxides of the acidity of your solution. Next, what about dissolving limestone in solution? Limestone, calcium carbonate. Is this more soluble in acidic or basic solution? So you can find a compound like this in the shells of corals and of other organisms at the bottom of the sea. So are these affected by having an increased concentration of protons, acidity, in the ocean? Well, actually, yes. Carbonate, which is produced by the dissolving of calcium carbonate, is consumed by protons to form bicarbonate. And so bicarbonate being formed, we lose carbonate, so this decreases the concentration of carbonate and shifts the reaction more to the right. This dissolving, this solubility of calcium carbonate is increased by having a more acidic solution. A similar problem involves your teeth. They are also dissolved better in acidic solution, and so if you have acids produced by bacteria around your teeth, plaque, then your teeth should dissolve a little bit. And so because hydroxide is part of your teeth, which is the part that reacts with protons, we can replace that hydroxide with fluoride from fluoride rinse. And having fluoride there instead, our teeth are much less soluble in acidic solution and therefore last much longer. We'll have fewer cavities. Thanks for watching, guys.